Welcome back everyone. In this video we can discuss about the universal gates. Basically this NAND and NOR gates. These two are known as the universal gates. Why? Why? Because using this NAND alone or using this NOR alone we can implement all other gates. That means NAND can be used for implementing NOT gate, AND gate, OR gate, XOR gate, XNOR gate, etc. Similarly, NOR alone can be used for implementing the same set of gates. So we can call these two as the universal gates. So in this video, we can consider how it possible. Okay, so the first one is the implementation of NOT. Whatever value applied to the input of this NOT gate, its output is the complemented form. Okay, so consider the simulation of NOT gate using NAND here. Similarly, NOR implementation for NOT gate. So this is the logic diagram corresponding to the exact NOT gate. Whatever value applied to its input side, its complement is available at output. 0 is applied here, output become 1. If 1 is applied here, output becomes 0. So now this one shows the NAND gate implementation for NOT. How it possible? To a NAND gate, its two inputs are connected with our input. That means the A value is supplied to both the input of our NAND gate. Okay, so its output part generate the complemented form of this A. Okay, so if A is equal to 0, then output become 1. Similarly, if A equal to 1, then output is 0. Okay. Similarly, the NOR gate implementation, NOT gate implementation using NOR. How it possible? Exactly like this. Instead of this NAND, here we are using NOR gate. If the input is 0, output become 1. If the input is 1, output is 0. So, these two are, this one is the NAND gate implementation for NOT. This is NOR gate implementation for NOT. Okay. So, now we can consider the next one. That is AND gate implementation using NAND and gate implementation using NOR. So, this is the truth table corresponding to AND gate. And if both the input equal to 1, then only the output become 1. In all other three cases, output is 0. Okay. So, first consider the AND gate implementation using NAND. So, for that what we want to do, apply A input and B input as the two inputs of a NAND gate. And its output is A and B complement. Okay, apply A and B as the input of a NAND gate. Output of that NAND gate is A and B complement. That output is connected as the two inputs of another NAND gate. Then it's generate A and B all complement. And between same two terms is equal to the term itself. That means A and B and A and B means A and B itself. The same way the output of the second NAND gate become A and B complement all complement. Okay, so these two complement get cancelled each other. Why? This is the property of complementation. Complement of complement is the original value itself. So consider this other implementation. That is NOR implementation for AND next. How it possible? Apply A input as an input of two input of one NAND gate and generate the complement. That means take an OR gate and generate the complement of A input. Take another NOR gate, generate the complement of B input. Now we have this A complement, B complement separately. These two pass through as the two different input of another NOT gate. So the output become A complement plus B complement all complement. Right. So while applying this De Morgan's law, what happened? This term become A complement all complement. This OR become AND. This one become B complement all complement. That is A and B. Now we can consider the simulation. So for this AND operation, this is the logical AND gate. If one of the input is 1, then output is 0. If both equal to 1, then only AND generate output equal to 1. So this one is NAND implementation using, AND implementation using different NAND gates. Okay, so what we want to do? So for getting this particular form, first apply A input as one of the input of NAND gate, B as the second input of the same NAND gate, and its output is A and B complement, which is connected as two different inputs of another NAND gate. So here it generate A and B complement and A and B complement all complement. And operation between two different terms is equal to the term itself. That is A and B complement, and A and B complement is A and B complement itself. And this is a NAND gate. So the output generated here it is A and B complement all complement. Now consider the complement property. Complement of complement is the original form. The exact output available here it is now A and B only. Now check whether this circuitry working as an AND or not. If both the input equal to 0, output is 0. If one of the input is 1, then output is 0 again. Like if 0 1 combination, output is still equal to 0. If both equal to 1, then output become 1. Exactly like our AND operation. Okay, next is AND implementation using NOR. Okay, so this is the case. First, generate the complement of A and B separately. A is connected as two input of one NOR gate. So here we have A complement. And similarly, B is connected with a NOR gate. Here we have B complement. So that A complement and B complement is passing through another NOR gate. Okay, A complement, B complement. So here we have this A complement plus B complement all complement. So while applying the De Morgan's law, A complement plus B complement all complement is A complement all complement and B complement all complement, which is available here, which is actually equal to A and B. Now we can check whether this working as our AND operation. If both the input equal to 0, output is 0. If one of the input is 0, still the output is 0. Okay, if both the input 1, then output is 1. Right? Exactly working as an AND gate. So from these two, we must remember one point, that is, for implementing an AND gate using NAND only, how many minimum NAND gates are required here? 2 NAND gates. Okay, and here for implementing an AND using NOR gate, how many minimum NOR gates are required? 3. Similarly, for implementing not using AND, not using NOR, how many minimum gates are required? Only 1. Okay. So next is the case OR gate implementation using NAND or gate implementation using NOR. Okay, so first consider this one. Similar to the AND gate implementation using NAND for getting A plus B. So from this truth table it is clear that if both the input equal to 1 and at least one of the input equal to 1, output of an OR gate become 1. If both the input equal to 0, then only output become 0. So here we need to generate the expression A plus B or A or B. Okay, so for that what we want to do, take one NOR gate, apply A and B as its input. So output of that NOR gate is A plus B complement. Pass that output as two inputs of another NOR gate. Then it generate A plus B complement plus A plus B complement all complement. OR operation between same two terms like this. OR operation between same two terms is the term itself. So we get as a final output A plus B complement all complement. These two complement gets cancel each other. So we have the final answer A plus B. Okay, this implementation is exactly like the AND implementation using NAND. Now we can consider this one, OR implementation using NAND, which is like our AND implementation using NOR. Okay, take the complement of A input, B input separately. Then pass these two, A complement, B complement as input of another NAND gate. Okay, so the result is A complement and B complement all complement. So apply the De Morgan's law. Now it become A complement all complement. This AND become plus B complement all complement. So while simplifying, these two complementation cancel each other, these also. So it is A plus B. Consider the simulation. Okay, so this is the OR gate. If both the input equal to 0, output is 0. If both equal to 1, output is 1. If one of the input is 1, then also output is 1. So this is this one, NAND gate implementation for OR. Take the complement, A complement, B complement separately using two different NAND gates. So here we have A complement, here we have B complement. These two connected as input of another NAND gate. So here we have A complement and B complement all complement. So while applying the De Morgan's law, we get A complement all complement plus B complement all complement here, which is exactly equal to A plus B. Now we can check whether this circuit working as our OR or not. So if both the input is 0, output is 0. If one of the input is 0, one of the input is 1, then output become 1. Okay. One input is 1, output become 1. If both equal to 1, output is again 1 itself. Just like this. So the circuit exactly working as our OR gate. So this is the NAND gate implementation corresponding to OR. So for implementing OR using NAND only, how many minimum NAND gates are required? 3. Okay. So this information is very important for objective type examination. So keep these points always in your mind. Minimum number of NAND required for implementing an OR is 3. Okay. So our next case, that is NOR implementation for OR gate. That is, we require two gates. First, here we get A plus B complement. So this A plus B complement is taken as two inputs of another NOR gate. So here we have A plus B complement plus A plus B complement all complement. OR operation between the same two terms, A plus B complement is equal to the term itself. So that is A plus B complement all complement. The complement gets cancelled each other and the final result is A plus B itself. Now we can check the input combinations. If both the input 0, output is 0. One of the input is 1, then output is 1. If both the input equal to 1, again output is 1, exactly working as our OR gate. So this is the NOR implementation for OR gate. How many minimum NOR gates are required for implementing such an OR gate? 2 minimum NOR gates. And in case of NAND implementation for AND, 3 minimum NAND gates are required. Okay.